So the last problem that we saw, it was LMTD method. So now this problem is based on solved through the ENTU method. So the ENTU method, so we will saw that some of the steps that we done in LMTD method are same as in ENTU method. So let's see what is the problem. So the problem is that the oil is to be heated in a double pipe heat exchanger from 32.2 degrees Celsius to 37.8 degrees Celsius. So it is to be heated. So the initial temperature is 32.2 and it is to be heated up to 37.8 degree to Celsius. The oil flow rate is 0.0504 kg per second and the water which is available at 65.6 degrees Celsius. So the water is available to heat up the oil. So the water temperature is higher than the oil temperature and so it is available at a flow rate of 0.63 kg per second. The heat exchanger is made up of uh, 2 multiplied by 1 1/4 standard type M copper tubing. So here this kind of a specification, you see this is basically 2 standard. The outer pipe is 2 standard and the inner pipe is 1 1/4 standard and the type M. So basically this is the specification for combination of a heat exchanger. And the tubing is 4.57 meter long. Analyze the proposed setup completely and use the effectiveness NTU method and place the oil in the annulus and oil properties at 35 degree Celsius. Okay. So in this type of problem, again the problem is that the final temperature for the oil, it is given that it is to be heated to 37.8 degrees Celsius. So we can take it this as T2 for the properties purpose. So the properties of the oil, we can find the average temperature, but for the properties of water we cannot find the average temperature because only the initial temperature of the water is given, which is 65.6 degrees Celsius, but the final temperature we don't know. That will come out from the calculation. In fact, the oil final temperature will also come out from the calculation, but it is given that it is to be heated to this temperature. So we can assume that the outlet temperature this is desired, so we can take it for the property purpose. Okay, so some of the steps will remain constant. So here the one more thing is, it is given that the use the oil place the oil in the annulus. So the annulus side the oil should be placed and the oil properties should be taken at 35 degrees Celsius. So they mention it clearly that what you need to do. So when we solve it, so again we will use the steady state analysis and the properties as per, like in this case oil case it is given as 35 degrees Celsius properties should be taken, and in case of water we can take properties at any point less than 65.6 degrees Celsius. You can choose 60, you can choose 50, whatever, and then the next iteration you have to check that the properties what is the final temperature come out to be and what is the mean temperature for the property purpose. Okay, so let's solve it. So you write down the properties of water, you write down the properties of oil, and as per the given specification for the standards and type, you find out the inner and outer diameter of the pipe, and you find out the inner diameter of the annulus, and then you find out the areas of flow for pipe side and annulus side, and then you find out the velocities. So these steps are same as you did in previous example. Again, that the hydraulic diameter and equivalent diameter calculation will remain the same as we did before, and same here the Reynolds number calculation, there is no change until now. So here what we can see that in the pipe side the flow is 55,000, which is turbulent. For the annulus side it is 5.26, which is a laminar flow. So you have to use the laminar correlation for the annulus side and you have to use turbulent correlation for pipe side. Okay, so based on the correlations you calculated the Nusselt number for pipe side, Nusselt number for annulus side, and So remember that the last slide we saw that this is laminar, so the laminar correlation should be used here, right? So uh, so we calculated the Nusselt number for both case, and then we calculated the heat transfer coefficient for the inner side, heat transfer coefficient for the outer side. So this inner side heat transfer coefficient, this one, is converted into the HP. So here we calculated the HP by multiplying the inner side heat transfer coefficient by IDP and divide by ODP. And then we find out the overall heat transfer coefficient through this formula, so which come out to be this value. So until this point our calculations are same. We start with the writing up the properties, and then writing up the size of the tube and annulus, then the flow area, velocity, and the hydraulic diameter, equivalent diameter, Reynolds number, Nusselt number, heat transfer coefficient, and overall heat transfer coefficient. So up to this point the calculation is same for LMTD and NTU method. So from this point onward the method is you choose and then it differentiate in calculation. So for ENTU method we need to calculate the parameter E, and the expression for the parameter E is this. And to calculate the E we need to calculate N and C. So C is the capacity ratio, that is the cold fluid capacity over warm fluid capacity. So this come out to be 0.037, and the N is the number of transfer unit, and this is the formula for number of transfer unit, U multiplied by A divided by MCP minimum. Remember here the C is the formula, the C formula is in the capacity minimum over capacity maximum. So the capacity for the cold fluid is minimum, and the capacity for warm fluid is maximum. So this is basically the min over max, which comes out to be 0.037. So when we calculate the number of transfer units, so this is UA over MCP minimum here. So after substituting all values, so here A is again the heat transfer surface area, which is the cylindrical surface area for the outer surface of the inner pipe, and which come out to be 0.502 meter square. And then you substitute these values in the number of transfer unit calculation, and then N and C you substitute here to find out the E. So remember that the E, we have two formula for E, one for parallel and one for counterflow. So here we are using it for counterflow. So we are applying the counterflow here. So once you calculated E, then you use the formula depending upon your condition. What condition prevails? If CPC is minimum, then the set of formula you choose is this one, and then you can calculate the outlet temperatures for cold fluid and warm fluid, and which come out to be these values. Okay, so now your outlet temperatures are calculated. Remember that in the question the desired outlet temperature was mentioned was 37.8, and when you analyze this heat exchanger for the given flow rate and for the given size, the outlet temperature come out to be 38.3 degrees Celsius, so which is little more than what we desire. Okay, so here the outlet temperature calculations are done. Now we want to make the heat balance. So for the heat balance we need to calculate what is our log mean temperature difference. So the log mean temperature difference, we can use the formula for the log mean temperature difference using the counterflow arrangement, and which come out to be 30.1 degree Celsius. Okay, so now we have the log mean temperature difference. So using the heat balance, we have three expressions, one for the heat transfer for warm fluid, and one for heat transfer for cold fluid, and one for the heat exchanger overall heat transfer coefficient expression. So all the three you can calculate, and which are come out to be almost is same all the case. So this is our check that everything is going right, the heat transfer rates are equal in all the three expressions. So this is the performance of the heat exchanger. You got the final temperature, you got the rate of heat transfer, you got the overall heat transfer coefficient. So remember that we have not until we have not taken any fouling factor into account. So if you take the fouling factor into account, then you have to find out that what is the fouling factor for the inner side fluid from the table, and what is the fouling factor for the outside fluid. And then you have to find out the new overall heat transfer coefficient. So this was the old, and then we are taking into account the following factors, and then we are calculating the overall heat transfer coefficient now. So we calculated the overall heat transfer coefficient now. So if for the same rate of heat transfer, because the overall heat transfer coefficient value is now reduced, before it was uh, 39.57 watt per meter square Kelvin, and now it is 39.46. So 39.57 and 39.46 was slightly smaller than the old value. So if you keep the heat rate of heat transfer same, and if you keep the temperature difference same, and you want basically the LMTD same, so you keeping everything same. So you want to see that if we want if we want the final temperatures to be same, not change, then what is the length of the heat exchanger required? So what will be the additional length, or what more length is required, as in the case of the old? Because in the previous case we have not taken the fouling factor into account, but now if you taking the fouling factor into account, then what length should it be? So you calculate the heat transfer area using this formula, that this is your new heat transfer area. Before it was 0.502 here, and now it is 0.503 here. So slightly increased area, and then you calculate the length using this formula. So the length is also slightly increased. So until now we have seen that we can calculate the final temperatures of the fluid flowing in the pipe and the fluid flowing in the annulus. We can calculate their exit temperature, outlet temperatures. We can calculate the overall heat transfer coefficient, and we can calculate the rate of heat transfer. Now the another parameters that we need to calculate for the heat exchanger is pressure drop. So how do we calculate the pressure drop for this heat exchanger? So the pressure drop formula for the pipe flow is same as we used to have in our pipe flow network. So the pressure drop formula, delta P, that the F over F multiplied by L divided by IDP, and multiplied by rho divided by 2 Vp square. So what we need to calculate here is, because the length of the heat exchanger we know, IDP we know, all the things we know except the friction factor F. So the friction factor F for the pipe side we will calculate based on the Reynolds number and based on the epsilon over IDP. So you calculate the Reynolds number for the pipe and epsilon over IDP, and then we can calculate the friction factor for the pipe side. For the annulus side, we calculate the Reynolds number for the annulus side. So the one important thing that you need to note here is that when you calculating the Reynolds number for the annulus side, then you have to take the hydraulic diameter into account. Hydraulic diameter. So the V annulus multiplied by the hydraulic diameter divided by the nu. So it come out to be 2.14. So both basically laminar. So, and this is epsilon over dH. So the friction factor comes out to be 29.9, which is very high in this case. And then you calculate the pressure drop. So this is your friction component, and this one is for your minor loss component, which is taken from the inlet and outlet, basically the inlet and exit losses together taken as one in this case. So this is how we calculate the pressure drop for our case. So now its analysis is completed here. So now this analysis is completed here. So we can see that the problem can be solved either by LMTD method or by an ENTU method, and we can calculate the pressure drop also. So this example is completed here. Now for the design of heat exchanger purpose, as we saw in the pipe flow analysis of pipe flow network cases, that when we and when we find out the diameter, so we need to use the economic velocity to choose the economic diameter. So here also for the double pipe heat exchanger, we will use the economic velocity to get the economic diameter, economic characteristic diameter or economic hydraulic diameter. So the range of economic velocities for different fluids we will take from this table, and we'll use in our heat exchangers. And the another table that suggests that what are the different possible combinations. So some of the combinations they mentioned here, that the 2 and quarter, 2 and half, and 1 and quarter, 3 and 2, and 4 and 3. So this indicate the outer pipe diameter, this indicate the inner pipe diameter, and then we have the various values like inner diameter. So this is in fit pond unit, and this is in SI unit. So this is inner diameter in meter, inner diameter of pipe, outer diameter of the pipe, and this is inner diameter of annulus here. And then the area of pipe, area of annulus, DH and DE. So if you're choosing the heat exchanger from here, then you can directly take these values from the table. You don't need to calculate the flow area and hydraulic diameter or equivalent diameter in this case. So this is completed here, and then in the next video we will see that how to solve the design problems related to double pipe heat exchanger. Thank you so much for this.